Hi, my name's Dr. Andrew Cullen from the University of Melbourne, and I'm here to present our work, It's Simplex, Disaggregating Measures to Improve Certified Robustness. This work was performed in collaboration with Paul Montague from DST Group in Adelaide, Australia, as well as Shiji Liu, Sarah Afani, and Benjamin Rubenstein, all from the School of Computing and Information Systems at the University of Melbourne in Australia. This work was supported by a DoD NGTF, an ARC DECRA grant, and our computing resources were supplied in part thanks to an ARC LEAF grant. So adversarial examples target inputs X of a classifier F to try and induce a change in that classifier's class prediction. So we'd like to find some new adversarial example X prime, which when passed through the model predicts a different class than when X is passed through the model. Of particular concern when it comes to adversarial examples are adversarial examples which minimize the distance between X and X prime. The reason why this is a concern is that this measure is treated as a proxy for our ability to detect the presence of an adversarial example, either through programmatic means or through human intervention. Now, the mechanisms that are used to construct these adversarial examples are typically derived from gradient descent, which makes them fast, easy to perform, and makes them require relatively limited resources. So, in response to the existence of these attacks, defenses have been proposed which attempt to either prevent an attack from taking place altogether or to increase the cost of an attacker trying to deploy an attack against a model, either in terms of their computational costs or financial costs or time costs. However, defenses are, at best, a response to a particular attack. They are not general and cannot be seen to be generalizable against all possible attacks. So what this means is that a motivated attacker just needs to find a threat vector that they can attack that has not yet been defended by the model defenders. And in doing so, the attacker will be able to completely evade any defenses that have been put into place. These defenses provide no guarantees of security. This observation about the nature of defenses and their responsiveness to attacks has motivated researchers to consider what is known as certified robustness, in which certificates that lower bound the distance between our sample point X and any possible adversarial example are constructed. So rather than looking at the distance to some adversarial example, a certified robustness certificate attempts to say that no possible adversarial examples can exist within a finite calculable radius. Doing so has two key advantages. The first is that it forbids the worst adversarial examples, the ones where X and X prime are close, that are very difficult to detect, and that can cause great damage to a model if allowed to go through. The second advantage of robustness certificates is that they can be used to rank samples by their potential risk. So if we have a set of samples with multiple different certificates associated with each sample, then the samples with higher certificates, which have a greater guarantee associated with them, are less likely to either A, have been attacked, or B, be attacked in the future, and as such, these samples probably will require less manual intervention, or can be passed through processes that require less screening and intervention. In contrast, samples with smaller certificates associated with them have a higher potential risk, both in terms of smaller adversarial examples potentially existing against these samples, and that it could well be that these samples have already been attacked. So we can use these certificates in several different ways to help us secure our models. Now, there are multiple mechanisms that have been proposed to construct these robustness certificates. One of the most popular mechanisms is known as randomized smoothing. Now, randomized smoothing, rather than passing a sample through our model once, we instead take our input sample, we add Gaussian noise to it of a fixed controlled standard deviation, and we pass that through the model not just once, not 10 times, but thousands or tens of thousands of times. And then we construct an expectation based upon the average performance of model samples being passed, of these model samples perturbed with Gaussian noise passed through the model. So the fact that we're passing thousands or tens of thousands of samples through a model to construct a single certificate makes this process slow and slightly non-deterministic because of the Gaussian nature of this. But the advantages of randomized smoothing is that it's easily parallelizable, It applies to any black box model F and imposes no additional limitations on the physical hardware required to construct the certificate. So what this means is that any model F that can take a sample X can always be used to construct a randomized smoothing-based certificate without requiring any additional hardware. This compares favorably to other techniques which typically require far more in terms of GPU resources to construct their certificates, or that they impose such significant limitations on the nature of the model F that it means that the certificate approach is not really general. So this is why randomized smoothing is so popular. Now, multiple mechanisms for randomized smoothing-based certifications exist, but the three most common or popular techniques are those of LaCoya, Lee, and Cullen. So LaCoya employed differential privacy to really first propose the idea of certified robustness, and their technique applies to both softmax and argmax style expectations. So softmax and argmax style expectations basically refer to how we treat the final layer of the model, and the formulas for these expectations, or how we approximate those expectations at any rate, are shown down below here. Basically, a softmax style expectation just takes the average of the softmaxes over the class set of the outputs, whereas the argmax style takes the argmax of each output, and so basically our expectation ends up being the count of times the particular class was selected divided by the number of total samples that we pass through. So LaCoya style certifications work for both softmax and argmax style output layers. Lee proposed an improvement to LaCoya's approach by instead using the Renier divergence, although their approach only is specific to argmax style expectations. And similarly, Cullen proposed further improvements over both Lee and LaCoya through the use of the Neiman-Pearson lemma, and again, their approach only applied for argmax style expectations. Now, one of the things that we noticed when we were investigating these mechanisms initially, and that kind of spurred this work, was the observation that the differential privacy-based mechanism that LaCoya used is quite a general mechanism. It's a very standard mechanism, but recent work has shown that actually that when the mechanism that the differential privacy system is built upon involves Gaussian noise, there are ways to tighten the guarantees provided by differential privacy, and so basically to produce a better measure of differential privacy, which is the conceit that is then used to build up the robustness certificate. So we then ask the question of ourselves of, okay, if we can take into account these new advances in how differential privacy is considered for Gaussian noise-based systems, could we improve the certificate that stems from the differential privacy? And so by taking into account the advances made by Ball et al., we were able to construct a new certification scheme, which is shown in these equations here, that makes it possible to uniformly improve upon the performance of LaCoya for both softmax and argmax style expectations, and also has some promising properties when compared with Lee's approach and Cullen's approach. Now, the fact that this involves solving a maximization adds an extra step of complexity compared to standard certification approaches. However, we must emphasize here that the surface that is being optimized over is actually quite a regular surface. It is quite a simple optimization to construct the global maxima to this, and that the computational cost of constructing this maxima is insignificant relative to the computational cost of constructing the expectations, which is really the dominant part of the computational cost of any randomized smoothing-based process. To analyze the performance of our new technique, we turn to a fairly common aggregate metric that is used across the certification literature, which is the certified accuracy. The certified accuracy measures the proportion of samples that have a certification greater than a given radius. So for example, at this point here on the blue line, we have a certified accuracy of about 0.35 associated with a radius of about 0.5. So this says that 35% of samples have a certified radius larger than 0.5. And so under this metric, larger numbers are basically better in terms of the y-axis. So if we look at the dashed lines, which correspond to the softmax style certifications, our technique uniformly outperforms LaCoya's technique. When we look at the argmax style certifications, our technique in orange outperforms Lee's approach and Cullen's approach up to a radius of about 1. And then after a radius of about 1, Cullen's approach ends up being the dominant approach. One thing, though, that we started to wonder when we were looking at these results was, well, if we've got multiple certificates, can we take advantage of the fact that we've got multiple certificates? What does it mean to have multiple certificates of robustness? If, considering that a robustness certificate is a guarantee that no adversarial examples exist within a calculable radius, if we have multiple calculated radii, then the largest of these radii is always going to be guaranteedly true, which means that basically if we have a set of multiple expectations, or sorry, multiple certifications, we can just take the largest of these certifications at any point to construct a guaranteedly best-in-class certification. And so that's what we did with this multinomial ensemble line, denoted with the circles, which captures the best-in-class performance of our technique for smaller radius adversarial examples, and then captures the performance of Cullen as the radius gets larger. And so we really take advantage of this very simple observation that when we have multiple certifications, we can leverage the largest of those certifications. Looking at the performance of these approaches, if we just look at strictly the performance of the techniques themselves, so Cullen, Lee's, and ourselves, Cullen's technique produces a smaller median certified radius and produces the largest certification more often than any technique for small levels of additive noise. But as we increase the level of additive noise, the median certified radius of our technique is larger than any other technique, and the proportion of samples where our technique produces the largest certified radius is also the largest of any other technique. And of course, the ensemble here on the right captures the best performance of all of these. So the ensemble will always produce a larger median certified radius than any individual technique, and will always certify more samples than any other technique as well, or any other individual technique. Now, of course, if I was to say that we're taking the maximum of 3 or 4 different certification techniques, and I've told you that certifications are quite a slow process to construct, you might wonder if it's really worth the extra time to make a small increase in the certified radius at the cost of having to repeat a slow process 3 or 4 times. However, a crucial observation is that the cost involved in constructing a certification is primarily in constructing the expectations, and the expectations can be reused across the different certification techniques. So what this means is that the cost of going from a single certification to an ensemble and taking the maximum of this ensemble is infinitesimally small, the difference between these two, relative to the cost of constructing the expectations, of passing the model samples, the samples perturbed by noise through the model again and again and again. And so what we've plotted here is the computational cost divided by the number of samples that we're passing through our model. And there is an incredibly small difference between any one individual technique and the computational cost of the ensemble. And this difference collapses as we increase the number of samples, emphasizing the fact that it is really the sampling process that is dominating the computational cost. However, at this point, we were really kind of wondering, okay, we have this set of we have this set of certifications, that are built upon the same set of expectations, and they do produce these different levels of performance, and we can capture the best parts of both by taking this ensemble. But we also wanted to understand why the different techniques were performing better. And this led us to our next development, which is the simplex of possible outputs, which is a way of understanding relative performance between certification techniques. So the simplex of possible outputs is a visual representation of the relative performance across the permissible space of outputs of our models. So in a certification sense, our models will be producing a set of expectations, which has a length equal to the number of classes of our dataset. And all those expectations must sum to 1. So we have this kind of constrained input space. And then we can restrict that input space for the purposes of plotting just the two highest class expectations, E0 and E1. The reason we can do this is because all certification techniques are built just considering the highest two class expectations. They don't consider the rest. So we can kind of map our permissible output space just down into the E0, E1 space. And then what we do with the simplex of possible outputs is we can exactly calculate the relative performance between our technique and any other approach at any point in this space, because the inputs to the certifications themselves are just the class expectations. And so if we go across all possible class expectations, we can map out the relative performance of different techniques. And so in this case, this plot here is the relative performance between our approach and LaCoya's approach for softmax style expectations. So for example, this set of class expectations maps to this point in the simplex of possible outputs, which says that our approach produces a certification 3 times larger than that of LaCoya's. At the most extreme point, our technique produces a certification that is over 5 times larger than LaCoya's for softmax style outputs. We can perform the same sort of analysis for argmax style expectations, where now our technique is compared to the largest of LaCoya's approach, Lee's approach, or Cullen's approach for an argmax style expectation. And what we find is that our approach produces the largest expectation in the region above the red line and to the left of the blue line. So in this region of the simplex of possible outputs. In the region below the red line, Lee's approach performs best, and to the right of the blue line, Cullen's approach performs best. And so now we've got this way of really capturing why a sample might be more suited to Cullen's approach or Lee's approach or our approach, based upon where it sits in terms of this simplex of possible outputs. This in turn allows us to kind of look in a disaggregated sense at what is happening when we pass a model and a data set through a certification framework. So these dots, green dots here in the right-hand side, are the location of outputs for ImageNet data passed through a ResNet model using randomized smoothing. And so what we can see is that there is a significant proportion of samples that exist in this region where Cullen is dominant, a small number of samples that exist in this region here where Lee is dominant, and a decent number of samples here that exist in this region where our technique is dominant over all others. And by dominant, I mean produces the largest certification. And so this kind of disaggregated lens gives us a tool that we can use to really understand the dataset influences, the model influences, the training influences on certification performance. Because we can see, okay, we're changing the output distribution of our model, and changing that output distribution then changes how different certification techniques will perform, and which techniques will perform better, which will perform worse, and why we see kind of changes in metric measures of certification performance based upon kind of these changes. It gives us another tool in our toolbox that we can use. So in summary, within our work, we updated the taxonomy of certifications to more clearly differentiate between softmax and argmax style certifications. We provided an update to the mechanisms behind differentially private certifications that yields improvements for both softmax and argmax style certifications. We demonstrated that multiple certifications can be used in parallel with incrementally small computational cost increases. And we introduced the simplex of possible outputs as a way to understand both the relative performance of different techniques and the drivers, including data-based drivers, model-based drivers, training setting-based drivers of certification performance. Now we'd like to just emphasize that this work sits alongside some of our other key works, including Double Bubble, Toil and Trouble, Enhancing Certified Robustness Through Transitivity, which shows how robustness certificates can be improved by exploiting the transitive property, and ET2 certifications, robustness certificates yield better adversarial examples about how adversarial attacks can exploit certificates of robustness to produce better adversarial attacks, which is a very surprising and concerning result. With that, on behalf of the authors of ItsSimplex, Disaggregated Measures to Improve Certified Robustness, I thank you for your time. Our paper can be found through the QR code embedded to the right. And if you have any questions, please feel free to email us through the email attached shown below. Thank you again.